Hello, everyone. We are PG Group 26, and we are going to introduce DQN and its several variants to you all. And our group members are Zhang Hao from AI track, Yihang from CS track, and Yilin from AI track. So let us introduce ourselves first.
Hi, my name is Zhang Hao, and this is my last term in my master's study. And we also have another group member, Zhang Yilin, but he already left this project because of the COVID restrictions. But he contributed a lot in the first part of our project, but he will not be in this presentation.
And I'm Yiha, and I will be the one who start the journey with you. So our presentation will compose the 4 parts. Firstly, I will briefly introduce our motivation of choosing DQN and its variants. And secondly, we'll go through the details of the 4 papers, including DQN, double DQN, prioritized experience replay, and DQN with dueling architecture. And then we will see the evaluation results of the 4 techniques to compare their performances. And finally, a brief conclusion of our work will be given. So DQN is proposed by the DeepMind team in 2015, and it combines deep neural networks with Q-learning. In Q-learning, when the state and action spaces are high-dimensional and continuous, using Q-table will cause a lot of time and memory consumption. So to solve this, DQN is proposed. And some DQN-related algorithms since then have been proposed on its basis. Therefore, we are interested in the underlying principles of DQN's variants and to see how they modify the original DQN. Also, we do experiments in gym environment to evaluate the performances of them. And next, we will go through the details of the 4 papers, which are DQN, double DQN, DQN with dueling architecture, and prioritize the experience replay. So as we've learned in the lecture, the key idea of deep Q learning is to combine use function approximation to represent the value function Q, and with the neural networks, the Q value can be represented as QSAW, where S is the state, A is the action, and combined with the neural network, we can represent the objective function as the equation 2 shows. And then the loss functions can be presented at the mean squared error, and the object can be written by the statistic gradient descent. And based on these ideas, there are mainly 2 issues. One is that there are correlations between the samples, and the second issue is that the Q learning in the Q value in the learning is non-stationary, so we have non-stationary targets. So deep Q learning addresses these challenges by 2 techniques. One is experience replay, and the other one is fixed Q targets. So the aim of experience replay is to break the correlations in data. This algorithm stores the transition ST, AT, RT plus 1, ST plus 1 in a replay buffer. And they will sample random mini batch of the transitions from the buffer, and then they optimize the mean squared error between the Q network and Q learning targets. So with the experience replay, the learning samples is enriched and the correlations between the samples are reduced. And to solve the problem of non-stationary targets, we need to fix the Q values targets temporarily. So therefore, we create 2 deep networks, W minors and W, and we use W minors to retrieve Q values and W to update the values in the training. So after a period of time, we synchronize W minors and W. In this way, we don't have a moving target, which makes the training easier. And DQN mainly solve the overestimation in the DQN algorithm, because DQN uses a target network to select the next action and use this action to calculate the Q value, which will lead to the overestimation. Therefore, in DQN, the action selection and action evaluation are decomposed. We use 2 networks to one is Q1 and the other one is Q2. Q1 network is responsible for selecting the action, and Q2 network is responsible for the evaluation. Based on this, the Q estimator in the target expression becomes Q1 and Q2 respectively compared to DQN. And for dueling DQN, it mainly changes the way of calculate the Q value. So let's go back to the meaning of Q value first. Q value tells us how good it is to be at state S and taking an action A at the same state Q, at that state. So the basic idea of dueling DQN is to decompose Q value into two parts. One is V and the other one is V, which represents the state value, and the other one is A, which is the advantage for every action. So dueling DQN are networks that separately compute the advantages and the value functions and combine them back to a single Q function at the final layer. So the architecture of dueling network is shown in the figure. One stream of fully connected layers output a scalar V, and the other stream outputs an A-dimensional vector A, and V and A together as Q. So however, we should never assume Q is a good estimate of the state value and A is a good estimate of the advantage value. So to avoid the estimation errors of A and V from being canceled out, we can subtract max A from Q, which is when the agents select an action by Q value, we guarantee this action has zero advantage value, and the value is shown as the second equation. And in the final implementation, the paper replaced max operator with the average, and the rank of actions in final Q value is not affected. So next, let our team member Zhang Hao introduce the other parts.
Now let me introduce about the prioritized experience replay. So uniform sampling from a replay buffer is a good strategy, but it can be improved by prioritized sampling. This will weigh the samples so that the important ones will draw more frequently from the training set. So the key idea is to increase the replay probability of experiences tuple that have a high expected learning progress, which usually means is a high training loss in the previous training. So how do we measure the priority? So we can just measure the TD error for DQN and the TD error for double DQN. The main difference here is that we are measuring in the double DQN, we are measuring the TD error of the evaluation network based on the selection from the selection network. There are two ways for getting the priorities. So we denote it as PI. One way is to directly use the proportional prioritization. We just use the TD error as our prioritization. And the second one is rank-based method. So we rank the TD error by rank, and then we use the inverted rank to calculate the rank-based prioritization. There are two hyperparameters related with prioritized experience replay, alpha and beta. Alpha determines how much prioritization is used in the replay buffer, and the beta is used when we sampling from the buffer, indicating how is also an indicator of how much prioritization is used. With combining of these two parameters, we can tune how much prioritization we want to use from the buffer. So we can find a balance between pure greedy prioritization and uniform random sampling. So here, when alpha is equal to 0, we use the level. We don't use any prioritization at all. So everything will be sampled uniformly. And when the alpha is equal to 1, everything will be sampled based on the prioritization. So now we have finished our description of our paper. we now introduce our evaluation setup. In the evaluation, we targeted on one game from the entire 2600 games breakout. So the first step, we are doing some image processing, and we perform a random start. Let the agent to randomly pick any actions. Then we use convolutional DQN to train the agent. We also talk about some hyperparameters we use and how we train the agent. So for image processing, we stack the 4 continuous frames from the gameplay. However, we only use one channel of the video, and we compress it into one channel using grayscale. We also crop the gameplay area to let the agent focus on the game rather than some borders and numbers, which may distract the agent's training. In the random start, we play 100,000 frames randomly. So we just use random choices based on the event ENV action spaces of the breakout, which contains 4 actions. And then we save the state, next state, reward, and done to the replay buffer. So we use convolutional DQN to train the model. For the regular DQN, we use 4 comp2D layer and 2 linear output layer. These parameters are found online, and we did some minor adjustments to fit our testing need. And for the dueling networks, we just added an extra linear layer and another linear layer with output size 1 as our advantage stream. The rest is very similar to the convolutional DQN setup. For the hyperparameters, we choose a set of values based on our several experiments and also some resources online. For the epsilon value, which determines how much random actions the agent might take, we use a start value of 1 and the final value as 0.05, and the epsilon value decays exponentially. For prioritized experience replay, we also use a changing beta value. Similar to the epsilon, we use the starting value of 0.3 and the final value of 0.001. For all of the variants, we use the same training strategy. So we run 3 million frames, and we use a batch size of 32, a fixed gamma and same optimizer, same learning rate, and same weight decay for all algorithms. And specifically for double DQN, we update the targets for every 1,000 frames. And for prioritized experience replay, we update the priority every 10,000 frames. So for the network training, we train for 3 million frames, and we record the reward loss and every 10,000 frames. So for the evaluation metrics, we are looking at the average reward at convergence, the speed of convergence, the stability of the model, and the scale of the trained agent. At the end of the experiment, we get a figure of our 4 different approach for DQN variants. As you can see in the frames, the double DQN showing in green is very volatile at the convergence rate, and the rate even dropped further at the end of the training. And for prioritized experience replay showing in pink is followed about the same trajectory as the original DQN, but it's more stable than the DQN, and at the end it converges at a much higher reward. As for dueling networks, the start is very quick, but the eventual convergence takes a long time. But the good thing about it is never seldom decreasing and always increasing in almost a linear pace. For the double DQN, there's it's slightly in between the other variants and dueling networks, but they also have a very low reward at the end compared to other networks. But more interestingly, we can look at the start of our training. So at the start of the training, we can see the dueling networks gain reward much faster than other networks. So take note here, the first 100,000 frames is random play. So even before random play, even a random play, the dueling networks can gain some advantage compared to other networks. And the vanilla DQN, which shown in green, grows the slowest among all of others. We also recorded down the loss during training. You can see in DQN and DQN with prioritized experience replay, they have very similar loss plots, which are very volatile, and they increase and decrease during the training. However, for DQN dueling, the loss will decrease very quickly, and it stabilize at a given range. And the very interesting thing about double DQN is that the loss increase a lot at the first 500K frames, and then it stay at the high value throughout the training. One potential reason is use two networks to one network to evaluate and another network to do the training. Now we can look at some video results. So we can see how the agent is actually playing the game. This is an untrained agent at the start with random action. So you can see that the agent can sometimes catch the ball, but they are just moving randomly without any experience. This video is recorded about 500K frames of training. You can see the agent is moving corresponding to the ball, but eventually at some reward will end the game because it cannot catch the ball or something. Then at the end of the training, the agent can play the game very skillfully and nearly misses a ball. But our training, the agent usually will lose the game after about 30 points, mainly because the agent is not skilled enough to score more points. So the agent actually never sees other higher stakes in the entire gameplay. Here's the conclusion of our project. The first thing is the vanilla DQN is not stable, as we can see from the reward graph. The reward is highly volatile, and sometimes it tends to overfit. And from our training, we can see that DQN with prioritized experience replay scored the best in the game breakout. And another thing we found out that not every variant outperformed DQN in every task. This corresponds to the author's finding in the papers we researched. And there are many other variants and modifications related to DQN we are not discussed here in this project, such variants as distributional DQN, noisy DQN, and rainbow network, etc. So this is the end of our presentation, and thanks for your time.